In this video, we will be learning about the ideal gas law and combined gas law. This will help you with the learning objective for calculating pressure, temperature, volume, or amount of gas by applying the appropriate gas law, because these two things have all of what we just learned in those simple gas laws incorporated together. We can combine those simple gas laws that we saw earlier into one massive equation. We learned from Boyle's law that pressure and volume were inversely proportional. And we learned that pressure and volume were both inversely related to temperature. And we learned that volume and moles of gas were also inversely related. So all of these relationships can be summarized in one formula as shown here. This also allows us to derive other combinations of variables that we didn't explicitly learn about in Boyle's law, Charles' law, Avogadro's law, or Gay-Lussac's law, such as the relationship between moles of gas and temperature, or pressure and moles of gas. Or what if multiple variables are changing at a single time? Now we can calculate it all in one equation. So just by remembering this equation, we can derive all of the other simpler gas laws. Because if we are ever in a situation where moles of gas is constant, then if we can write if n is constant, then our n1 will be equal to n2, and then those terms would cancel out. And similarly, if any of these other variables is constant, then it will cancel out. So in Boyle's law, n and t are constant, and so both of the n1s and t cancel out. And then Charles's law, n and p are constant, so those cancel out. Avogadro's law, the p and the t are constant, and you're only left with v and n. So we can derive all of these other simple gas laws into one. And personally, I don't really care too much about like which law is which, because this combined gas law has it all. Using that equation from the previous slide, you can see here that we isolate it all onto one side of the equation, and then we set this equal to R. R is known as the ideal gas constant. And so rather than solving for pressure, volume, nitrogen, like moles of gas and temperature at one time point and then changing variables and solving for it at a different time point, we can just say what is it at one time point. And so you can see here that if we had our PV equal to nRT, we can rearrange the n and the t onto the side of the equation and have that equal to R like it was on the previous slide. This is known as the ideal gas law, and this is the equation that we'll be using whenever conditions are not changing. So if we're given only one pressure, one temperature, one volume, we could solve for moles of gas. So this is awesome. R is the ideal gas constant. R is on your yellow sheet. On your yellow reference sheet. R can be expressed in a variety of different units. You should always make sure that you're looking at the units of R. And so all of these are different. Well, they are the same value of R. They're just expressed in different units. So you can always pick your R to match your units so that you don't have to do as many unit conversions. So if you are using this R, which is in liter atmospheres per mole Kelvin, this tells you that in order for your units to cancel, your volume has to be in liters, your pressure needs to be in atmospheres, and your temperature needs to be in Kelvin, and moles of gas always needs to be moles of gas. So a general strategy for applying the ideal gas equation is collect your information given and look to see what units you're given and whether you need to do any unit conversions in order to match your value of R that you've selected. If you always like to use the value of R that's in liter atmospheres per mole Kelvin, then you're going to need to match those units. Or you can pick an R that matches the units that you're given more closely to minimize your unit conversion life. Identify what variable you need, and then you can use algebra to isolate the variable that you're solving for and plug in variables. But you also need to be able to decide whether do you use the combined gas law or do you use the ideal gas law. So let's look at this example and decide which equation we need to use, and then we can identify our variables and plug them in. This says a balloon is filled to a volume of 2 liters at room temperature and pressure, and then it gives me room temperature and pressure. Then the balloon is placed in a freezer, and pressure is staying constant. So P is constant, but my temperature is changing. So my T is changing. What is the final volume of the balloon? So this is telling me that I need a relationship between different volumes and different temperatures. And so T and V are changing. So I'm going to say use combined gas law. We want to use the combined gas law whenever temperatures and stuff are changing. Whenever values are changing, that's when we want to start with our combined gas law. So here's our combined gas law. We know that P is constant. That means that P1 is going to be equal to P2, and so that those two terms will cancel out. If I divide both sides by P1, P2 divided by P1 is just going to be 1, so that's going to cancel out. It doesn't mention moles of gas, and so I'm going to guess that this balloon is tied shut, and so our N1 is equal to N2. Constant means they're not changing, and so then I'm left with V1 over T1 is equal to V2 over T2. I'm asked to solve for a final volume, and so that is V2. So that means that my V2 is going to be equal to V1 over T1 times V2, T2. So now V2 is going to be equal to my initial volume, which is V1 over here. That's 2.0 liters. My final temperature is this negative 17 degrees Celsius. And so I need to convert that into Kelvin. Temperature always needs to be in Kelvin for gases. Well, that is so not what I meant to type in. Negative 17 plus 273.15. And that's going to be 256. That is only significant to the ones place, so I'm going to underline that so that I remember. And then my T1 is 27 degrees Celsius. So 27 plus 273.15 is going to be 300.15 Kelvin. And then underline that so that I remember. So my V2 is equal to 2 times 256.15 divided by 300.15. And so that will be 1.7068. I need two significant figures, and so that will be equal to 1.7 liters. We could have made that prediction by looking at the temperature, and so since temperature drops, my volume should drop. And so that's the conceptual relationship given to us by, I think it's Charles's law. So we know that our V2 should be lower, and it is. Here's a conceptual practice problem for you. If you take a 4-liter container of gas at 300 Kelvin and compress the gas to a 2-liter volume and simultaneously heat the vessel to 600 Kelvin, what will be the final pressure of the gas? Go ahead and pause the video and to think about this, and when you're ready to check your work, then unpause the video and let's think about that. Okay. Our pressure is going to quadruple. That's because our temperature is doubling. And so since our temperature is going to double, then our pressure is going to double. Then our volume is getting cut in half. So since our volume is getting halved, then our pressure is going to double. So we're doing two things that independently double the pressure. So a double and a double is a quadruple. That means it's going to be whatever our initial is times 4 is going to be equal to our final. You can also solve this problem mathematically by inserting the numbers given and solving for P2. P2 is going to be equal to 4 times P1, and so that means that your final pressure is going to be 4 times P1, which is quadruple of P1. Here's a second practice problem for you. If you take 2 liters of this and then you both double the volume and the temperature in Celsius, what happens to the pressure of the gas? Go ahead and pause the video and try to work this out, and then unpause the video when you're ready to check your work. Okay, so let's go over this. I'm going to solve this problem mathematically because I know that these temperatures really need to be in Kelvin. And so this is not even, though we are doubling the Celsius temperature, we are not doubling the Kelvin temperature. And that's going to make a big difference. And so that's 323.15 Kelvin. So we know that we are doubling. We're going to start with our combined gas laws since we got a lot of things changing. And we are solving for P2 here. Our initial pressure, we are not given. We have to figure out P2 relative to P1. So P1 is equal to V1, which is 2 liters. And we have our N1 here. We are not given N1. N1 must be equal to N2, so that will cancel out. And T1 is equal to 298.15 Kelvin. And so we are solving for P2. And so that means I'm going to be multiplying both sides by the reciprocal of this other part in order to cancel out those terms. So to isolate P2 on this side, I'm going to need to multiply by T2. And divide by V1, V2, which is 4 liters. So we can see that that's going to make a nice pretty fraction of 1/2, but that's not going to make a pretty fraction. So let's just calculate this. We got 323.15 times 2, and then our denominator is going to be 4 times 298.15. And so that means that P2 our final pressure is going to be 0.542 times P1. That's not quite 1/2. It's pretty close, but not quite 1/2. We're going to go with none of these answers because it's not really 1/2 of P1. So by doubling the Celsius temperature, we are not doubling the Kelvin temperature. Here's another practice problem. This one reads, dinitrogen monoxide is laughing gas used by dentists as an anesthetic. A 20-liter tank of laughing gas contains this many moles of NO2 at 23 degrees Celsius. What is the pressure in the tank? So since I'm only given a limited number of variables, I can know I'm going to be using the ideal gas law. Things are not changing. And so I'm going to be using PV is equal to nRT. So I'm just going to write out PV nRT off to the side here and identify my variables. L is liters, and so that's a volume. I am given moles of gas. And I am given a temperature of 23 degrees Celsius, and I know I got to convert that to Kelvin. I always have to convert my temperatures to Kelvin. So that's 23 plus 273.15, and so that's going to be equal to 296.15, and I'm just going to underline the ones digits so that I remember that that was the last sig fig. It's asking me for the pressure in the tank, so that's what I'm going to solve for, and then R is an ideal gas constant. Since it doesn't tell me a pressure unit, it kind of is my choice what R value I use, but I see that my volume's in liters, and so I'm just going to use the constant that is 0.082058 liter atmospheres per mole Kelvin. Sometimes that's rounded to just 6, but that's the more sig fig version of it. If you use these values enough, you just kind of memorize them just from it being overused in your brain, not because anyone actually told you to use them or to memorize them. So PV is equal to nRT. So if I divide both sides by V, then that cancels out, and I'm left with P is equal to nRT over V. So now I can plug in my numbers. That's 2.86 moles. R is 0.082058 liter atmospheres per mole Kelvin. And then my temperature was 296.15 Kelvin. And then my denominator is my volume, which is 20 liters. So that mole cancels with that mole. That atmosphere doesn't cancel with anything. That liter cancels with that liter. Kelvin cancels with Kelvin. My answer will be in atmospheres. So my answer is 2.86 times 0.082058 times 296.15 divided by 20. And so that is going to be 3.475 atmospheres. This has 3 sig figs, 3 sig figs. That was significant to the ones place, though that has 3 sig figs. I need 3 sig figs. That's going to round up to 3.48 atmospheres. Here's a practice problem for you. Go ahead and work this out on your own, and then unpause the video when you are ready to check your work. Okay, let's go over this. It says a size 7 basketball, that's kind of irrelevant number. I don't care what size basketball it is. Has a volume of this and is inflated to a pressure of that, at a temperature of this. How many moles of air are inside the balloon? So since temperature I'm only given one pressure, one volume, one temperature. Things are not changing, and so I'm going to use the ideal gas law, which is PV is equal to nRT. I am asked to solve for moles, which is N. That means I need to rearrange this equation to solve for N. Got to divide both sides by RT, and I'll end with N is equal to PV over RT. I'm going to identify my variables off to the side here. PV is equal to nRT. This is a pivnert. And so my P is 8 psi. My volume is 7.10 liters. My moles is what I'm solving for. My temperature is 27 plus 273.15. And so that's 27 plus 273.15. That is 300.15 Kelvin. So looking at this, I can see that I do not know my R yet. That's in PSI, and I'm given this hint here about atmospheres. So I could go ahead and convert this into atmospheres by canceling out my PSI and getting me into atmospheres. This means that my pressure would be in atmospheres. So the R I should use should be in atmospheres. So I will use the 0.082058 liter atmospheres per mole Kelvin. And I will calculate the PSI value. So 8 divided by 14.7. I'm going to go ahead and store that value. And so that's going to be equal to 0.544 atmospheres. So now I can plug into my rearranged algebra equation here. I need my pressure. I'm going to use the full pressure even though I did only write 3 digits there. I am going to use that full calculator output because I never want to round my numbers until the end. And so I never want to use rounded numbers in a calculation because then I could end up with some really weird rounding errors. Okay, that's a K. Use your imagination. So now I can plug in my numbers. I saved my pressure as A, and so I can type that in. So double checking calculator entry, all looks good. And so that works out to N is equal to 0.15688 moles. And I need to double check my sig figs. This had 2 sig figs, and that had 3, and that's going to be significant to the ones place. So that's going to have 3. So I'm going to need 2 sig figs. This pressure only had 2 sig figs. And so I'm going to round that to 0.16 moles. Here's another practice problem for you. It reads, a mason jar with fixed volume is filled with jam at room temperature of 27 degrees Celsius and a pressure of 1 atmosphere, leaving 38 milliliters of gas in this region that's known as the headspace of the jar, between the jam and the top of the jar. The lid is left slightly loose to allow gas to escape. The jar is then loaded into a boiling water bath canner at 100 degrees Celsius. And if the pressure and the volume remains constant, how many moles of gas escape the jar? Go ahead and pause the video and try to work this out on your own. Unpause the video when you are ready to continue. Okay, so we do see that things are changing. We are changing temperature and we are changing moles because it's asking about moles. So we are changing things. And so that means we should use the combined gas law. And so that is P1V1 over N1T1 is equal to P2V2 over N2T2. It says that pressure is constant, and it says that volume is constant. So that means I'm left with 1 over N1T1 is equal to 1 over N2T2. And I can rearrange that equation so that N2T2 is equal to N1T1. We haven't seen a gas law that said this relationship, but this is the relationship that we're going to be using in this equation. So my N2 is what I'm solving for. So N2 is going to be equal to N1 over T1 divided by T2. I'm going to be needing to solve for my final N, but that's not going to be my final answer. It's asking for how many moles escaped. So I'm going to have to do some subtraction here to figure out final minus initial, like how much did that change. But one thing at a time. I'm not even given my initial N, am I? I'm going to have to solve for N. So I'm going to have to use PV equals nRT solve for N1. I'm not even given N1. I have to solve for N1. N1 is going to be equal to my pressure, which is 1 atmosphere, and my volume. I'm going to have to convert that into liters. PV over RT. I'm using atmosphere, so I'm going to use the 0.082058. And then my Kelvin temperature of the initial is 27 plus 273.15. And so that's 300.15. So my initial moles is going to be equal to 1.00 times 0.038, 0.02058 times 300.15. And so my initial N is 0.00154, blah, blah, blah. I'm going to go ahead and store that number in my calculator, so I don't have to type it in again. So that's my N1. So now that I actually have an N1, I can plug that into where my equation is for N1. And then my T1 is going to be that temperature there. And then my T2, I didn't calculate that. I can calculate that in my head. So that's 100. I got to convert that to Kelvin. That's 373.15 Kelvin. So I need to take my initial mole amount, and I got to multiply that by 300.15 and divide by 373.15. And so that tells me that my final N is equal to 0.00124 mole. Now I can look at these two mole amounts. It's asking for the change in moles because it's asking about how many moles escaped. So to look at how many escaped, I can see this is how many I had initially, this is how many I had final, and I can subtract the two. And so I'm going to do escaped is equal to N1 minus N2. Did I save that number? I did not. So that is It's typing in more digits than I need. I forgot a 0. See, this is why you should save your numbers in your calculator so that you don't have to retype all this stuff. I can see that those first ones line up, so I know that they're going to subtract out. But now I got to scroll back up so I can see my previous entries. There was only one there. And I forgot the 4. 124102. See, I just need to get in the habit of saving my numbers. So I'm going to convert that into scientific notation. And so that is going to be equal to 3.018 times 10 to the minus 4th mole escaped. A very tiny amount of moles escaping the jar upon heating. Now that we know that, I have to think about sig figs. That had, the volume only had 2 sig figs, so that means that this whole nonsense here has just 2 sig figs. And that is also, that's going to have 3 sig figs, but that's going to leave this significant to only the 5, and so that's going to be just the 3. So rounding for sig figs is only significant to that decimal location. So that's 3 times 10 to the minus 4th moles escape the jar. Last practice problem, I swear. This one reads, one of the cylinders of an automobile engine has a volume of 350 cubic centimeters. The engine takes in air at a pressure of 98.0 kilopascals and a temperature of 15 degrees Celsius and compresses it to a volume of 45.0 centimeters cubed and 110 degrees Celsius. What is the final pressure of the gas in the cylinder? Go ahead and pause the video and try to work this out on your own. Unpause the video when you are ready to check your work. Okay, since things are changing, use the combined gas law. So we got to use this combined gas law here. So now we got to plug in our variables. So this is V1 and this is a pressure. So that's P1 and that is T1. And then we are compressing it to this, which is V2, and this temperature, which is T2, and asking us for the pressure. So we are solving for P2. It tells us nothing about N1 or N2, so we're going to say that that's constant in this process. And so now we've simplified our combined gas law to give us the relationship we want and need. I can go ahead and plug in my variables, 98.0 kilopascals, and then I will have my volume initial, which is 350 centimeters cubed, divided by T1, which I need to convert into Celsius, not into Celsius, into Kelvin. We were always using Kelvin. And so that's that side of the equation. Now I can come over to this side. I am solving for P2, and that is V1, which P2, which is 45.0 centimeters cubed, and that temperature, which I got to convert into Kelvin again. And so my P2 will be equal to 98.0 times 350 times 383.15 divided by 288.15 times 45.0. And I didn't put units on, but I can go back and I can do that. So I got my 98, and I got to multiply that by 350, and then multiply that by 383.15, and then I got to divide by 288.15, and then you got to make sure that you're also dividing by that volume. And so that says that my P2 is 1013.5 kilopascals. That's a big kilopascals. And so I got to think about my sig figs. That had 3 sig figs, 3 sig figs, 3 sig figs. So even though my temperatures, that had 2, but by the time it's converted into Kelvin, it will now have 3. So I'm applying my multiplication rule. I'm going to need 3 sig figs. And so I'm going to report this in scientific notation. 1.01 times 10 to the 123 kilopascals. 1.01 times 10 to the third kilopascals.